Good morning. I am Prabhu Benmarat, Assistant Professor, Department of CSE, BAd CET, Vijaypur. So in this video, I am going to discuss about the chi-square goodness of fit for Poisson distribution. So let us first understand in which step the goodness of fit test will be applied. So this flowchart shows the steps for development of useful model of the input data. So first we will collect the data from the real world system of interest. We will identify the probability distribution to represent a input process. In third step, we choose a parameter of a distribution family, and in fourth step, we will evaluate the chosen distribution and associated parameter for goodness of fit, right? So we are going to apply the chi-square goodness of fit test at fourth step. So at fourth step, we will be having a probability distribution, the distribution, different distribution, as well as the associated parameter with respect to what here, the collected data, right? Using the chosen distribution and the particular parameter, we will apply a chi-square test whether that data will accept the chosen distribution or not, will follow the chosen distribution or not, or assumed distribution or not. So that we are going to check here, right? So one more important thing we have to remember is parameter estimation. So the parameter estimation is nothing but finding the sample mean and sample variance of a randomly selected data. So it is not possible to apply the test for entire population of a data. So what we do, we choose randomly some information from the entire population, and on that population we will estimate some of the parameters such as variance and mean of a data, right? So this table shows the parameter and estimator for different distributions. So when the Poisson distribution is assumed, so we are looking for the parameter alpha, and how it is estimated, that is alpha cap equal to x bar. And if the distribution is assumed as exponential, then the parameter is what here, lambda. The lambda is calculated, that is estimator is calculated such as lambda cap equal to 1 divided by x bar. So here cap indicates the estimator, okay? So in case of gamma, we will find out two parameter, and in case of normal distribution, we will find out two parameters, and those two parameters are estimated in this way by using these equations. And in log normal, we are going to find two parameters, that is mu and sigma square, right? So here in case of Poisson and exponential distribution, we are just finding what here, only one parameter, right? That is alpha cap and lambda cap. So these are what here, the way how we are finding the estimator alpha cap and lambda cap, okay? So let us consider a problem statement, how goodness, chi-square goodness of fit test will be applied, right? So the problem statement is apply chi-square goodness of fit test to Poisson assumption. So what is the type of the distribution we are assuming? Poisson assumption, Poisson distribution with alpha cap equal to what here, 3.64. So the estimator value they have given along with the problem statement, and the size of the data is how much here, 100. The data they haven't specified here. So the data value they have not given along with the problem statement, right? But they have given what here, the size of the data and observed frequency. See, after looking it into data, so how many frequencies they have observed, in which range how many data they have observed, that they have given here, that is OI equal to all these values, and the level of significance is alpha equal to 0.05. So considering all these values, we have to estimate, we have to find whether the given data, nothing but the observed frequencies, will follow the Poisson assumption or not, Poisson distribution or not, right? So the first step is what here, we have to form the hypothesis. So the first hypothesis is what here, H naught, that is the random number distributed as a Poisson, and H1 is what here, the random number is not a Poisson distribution, right. So our aim is to test whether the given data is rejected or not, that is null hypothesis is rejected or not, that we have to find, right. So in second step, what we do, they have given, see, along with the problem statement, they have given the parameter estimator. So no need to find out the value of this parameter estimator. So directly what we do, we will go to second step. In this step, what we do, we find the theoretical hypothesized probability for each interval using PMF of Poisson distribution. So you have to find theoretical hypothesized probability for each class interval, right. So by using what, PMF of Poisson distribution. So why we are using PMF of Poisson distribution? Because the data has been assumed as a Poisson distribution. So this statement has been given along with the problem statement. So that's why we are considering PMF of Poisson distribution. So probability mass function. So this is equal to P of x equal to e raised to minus alpha, alpha raised to x divided by x factorial. So where x starts from what here, 0, 1, 2, 3, so on, right. So the first theoretical hypothesized probability is nothing but P of 0 equal to e raised to minus 3.64. This is what here the value of alpha cap, which is given along with the problem statement, right, into 3.64 raised to 0 divided by 0 factorial, we get the first class interval theoretical hypothesized probability value as a 0.026, and we will find out the second theoretical hypothesized probability for second class interval, that is e raised to minus 3.64 into 3.64 raised to 1 divided by 1 factorial. This is equal to 0.096. So we will find out the theoretical hypothesized probability values for each class interval. So the last class interval is having the value 0.001, right. So after finding the theoretical hypothesized probability values for each class interval, the next we have to find is what here, what is the expected value in each class interval. So this is calculated by EI equal to n into PI. So the n is nothing but the total size of the data, that is 100, into PI is nothing but the theoretical hypothesized probability value of each class interval, right. So that is E naught equal to 100 into 0.026. So we get 2.6 is what here expected value in first class interval, right, and this is expected value in second class interval, expected value in third class interval, so on. The expected value in last class interval is how much here, 100 into 0.001 equal to 0.1, right. So I repeat here. So first we have to find out what here, theoretical hypothesized probability for each class interval by using PMF of Poisson distribution, and after that we have to find out the expected value in each class interval using EI equal to n into PI, right. So in last step what we do, we use the chi-square statistical computation equation for finding what here, the statistic value, chi-square statistic value, that is xi. So what is the equation here, summation I equal to 0 to k oi minus ei bracket square divided by ei. So this is what here xi is nothing but what here, class interval, oi is nothing but observed value, ei is nothing but expected value in each class interval, right. So list out, so xi always starts from 0, so that right from the 0 and last value is how much here, greater than or equal to 11. So oi value is given along with the problem statement. So what is the observed value in first class interval, that is 12. The observed value in second class interval is what here, 1. The observed value in the third class interval is what here, 19. So on you write down, and after that you have to write expected value which is calculated just now, right? And after writing all expected value, so the next step is you have to check the expected value which is less than 5, and if it is less than 5, then you have to combine that expected value with what here, the adjacent expected value. So let us start from beginning. So the first expected value is 2.6, which is less than 5. So therefore you combine this with the second expected value. So we get how much here, 12.2. So the third expected value is above 5, so no need to combine. So this is also what here, not less than, this is also not then less than 5, this is also not less than 5, this is also not less than 5. And coming to eighth one, so here 4.4 is less than 5, so that combine all these values, group all these values, and we get how much here, 7.6. See, after combining the expected value which is less than 5, next you have to group or combine the observed frequency of corresponding expected values. So here 2.6 is combined with 9.6, so that the corresponding observed frequency you have to combine. So 12 and 10 we have combined, we get how much here, 12. So similarly, so these last 4 values, expected value we have combined, the corresponding observed value we have to combine. So we get how much here, 17, right? So after this you have to find out OI minus EI bracket square divided by EI, nothing but, so in case of first value, so what is OI, that is 12 minus 12.2 bracket square divided by 12.2, we get how much here, 7.87. So similarly you find out for all the class intervals, right? So after finding the OI minus EI bracket square divided by EI value for all the class intervals, you have to add all these values. So we get 27.68. So this value is called as what here, chi-square statistical value, right? So this value you have to compare with the critical value, that is the degree of freedom for chi-square test is chi-square alpha comma k minus s minus 1. So here k is nothing but the number of the class intervals after grouping. So earlier we had 12 class intervals before grouping. So once after grouping with the adjacent class class intervals, so we got how much here, 7. See, this is 1 2 3 4 5 6 7. So 7 is nothing but what here, the value of the k, and s is nothing but the number of the parameter for Poisson distribution. So how many parameters we are estimating here? Only one parameter, that is alpha cap equal to x bar. So 1 you have to take for s, and minus 1. So what is the value we get here? That is chi-square 0.05 comma 7 minus 1 minus 1. So we get chi-square 0.05 comma 5. So this is obtained from the table, right? So we get value 11.1. So this 11.1 is compared with what here, the computed value. So the computed value is what here, greater than the 11.1, so that the null hypothesis is rejected. Thank you. Please subscribe to my YouTube channel to see more videos on system modeling and simulation.